Hi, everyone. Thank you for being here. We're going to get started. We're very excited to show you some of the latest thinking about this is one of the really cool innovation we have. So my name is Bo. I'm a product manager from Google. Today I'm joining with my colleague John Belamaric, who is a senior staff software engineer from Google, and we're going to show you about the latest thing we're building to really help you out with manage the GPU resource to better run your inference and any other AI machine learning applications. All right, without further ado, let's get into that. First, let's look at one real-life example. If you have been there, you will see the feeling of that. If you haven't, I think you're probably going to get into that situation very soon. All right, imagine I'm running a inference sort of application, which is a shopping bot for a shopping platform. And the shopping platform is running a shopping festival, really, which is really going really well. We're putting the big sales numbers, and then people are, in general, very happy. But at the same time, as the sales keep getting more and more hot and more popular, and I noticed something as the infra team. So right now, I'm actually using like A100 to serve this inference workloads, and then this shopping bot can help the customer to really answer questions and promote a product. Is really critical for the sales and for the business success of the company. But then when the application keep being scaled up, I noticed that because the GPU is still a very scarce resource, it's sometimes really hard to get the model you want. And well, all of a sudden that my A100 is no more available. So I'm hitting a stockout issue for my application. What I'm going to do with that? All right, when I look at, when I think back, I can actually make this application work with maybe 2 L4 GPUs. And then look at my the stack of the GPU that I have. I can maybe make that work with 3 T4 GPUs as well. All right, I'm good at this. I'm just going to create 3 deployments, and then just using 3 machine types separately, manage that, problem solved. I can just lean back and have a cup of coffee. We know that's not the case in reality, right? The business is changed very quickly, very dynamically. And in this case, we say, hey, one of the vendors that get really popular on this shopping platform is launch a flash sale for 2 hours. And this just triggers hundreds of thousands of customers get onto the platform and want to find out more about the application, of the goods that we're selling. Now I need to really think about how do I scale up my application. And also the problem is that because this is a flash sale, it's going to take about 2 hours, and after that it's going to run down. I don't want to have my resource to sit there for a very long time, because we know that GPU resource is way more expensive than the traditional CPU and memory. So how do I do with that? And think about how do I scale up immediately? And then when I have all these applications being scaled up, how do I track the quota of each GPU? Because I can use at least 3 types of GPU in this scenario. And then do I need to, throughout this whole journey, I need to change the quota of each GPU type the whole time? And also, when the services start to slow down, I actually prefer to have more more pods that remain on, let's say, the A100, because that's the preferred platform. It has better cost performance. How do I do this? And then if I just want to, if I have the application running on multiple GPU platforms, can I move that from one platform to the other one to just balance things out? This will be my face after handling all these, after quite for 5 minutes. So how should I solve this? There must be a better way to do that, right? So we're looking into this and say, we should actually solve this by having a means to allow developer to consume GPU resource in a more flexible way. And then with all the limited resource you have from the different GPU models and stack, we should find a way to improve the obtainability. And then we should really make the developer's life much easier. So that's how we start with the DRA, Dynamic Resource Allocation. And this is sort of a short way to look at the design principle of this product. Flexibility-wise, we want to make sure that you can use the same GPU resources to serve different applications that improve the utilization of that. It will help you to lower the cost independently as well. And then also the other way around, you want to make sure that you can easily use multiple and different type of GPU to serve your applications. And then efficiency, obtainability, as we touched on earlier, it's one of the biggest problems. Let's solve that. If you can flexibly use different GPU type, it solves your obtainability issue as well. And then lastly, ease of use. Because if the product is hard to use, you won't really get adoption. In this case, using the declarative way of Kubernetes to help developer to consume this product, and all we want to see is your happy face on the right-hand side, instead of the sad face that we just saw minutes ago. So that's how we come with this design, and we want to stick to this way to help you run your inference workloads. And then now let me hand over to my colleague, John, to share more about this feature.
Thank you, Bo. As Bo said, Dynamic Resource Allocation, or DRA, this is an upstream open source Kubernetes feature we've been working on for some time now. And one of the things it does is increase the flexibility in the way that a single deployment or pod can ask for GPUs, and you can fulfill that request in different ways. This is in beta right now, but we are working actively to get it to stable in 134, which should be released in August. So we're pretty excited. And to kind of give a little bit more detail on what we mean by or how DRA works, essentially it's broken into 4 parts. The first part is a new way to describe the hardware as opposed to the existing mechanisms in Kubernetes, which is called device plugin, allows you to use a string and an integer. If you were in the presentation just before this one, this was discussed quite a bit. It's very limiting. You can just basically give a name and an integer for the number of devices that are on a given node. With DRA, we create a new, actually upstream API resource called a resource slice, which has a pretty sophisticated modeling and getting more sophisticated modeling API for vendors to represent their devices. So instead of saying I have 5 NVIDIA devices, I can say I have 5 A100s, and the A100s in this configuration have 40 gigs of memory, and they're on this driver version, and et cetera, et cetera. I can attach a bunch of metadata, and in future releases we can even do more. The second half of this, and the reason 1 and 2 are bolded here, they're the ones most interesting to end users, and number 2 in particular is the thing that end users would actually write. So this is our resource claim API. So the resource claim API is how you ask Kubernetes to give your pod those resources. And so, again, in existing Kubernetes, you would just say request or limit, you'd say nvidia.com/GPU2. Just like the advertising of the devices, the request for the devices is just a string and a number. In DRA, we make that a whole object, a resource claim object, which allows us a lot of flexibility to ask for not just groups of devices, but criteria-based requests, like give me any GPU with at least 40 gigs of memory. So now that's an NVIDIA GPU, right? So then now, even if you don't have any exact A100 40 gigs, but you have some 80 gig ones available, your workload can run. So that kind of flexibility, both on the richness of the API for the vendor to specify how their device works or what it looks like, and the richness of the API for the user to request enables a lot more functionality. The second 2 parts are really implementation details. Once you've got a new flexible API for asking for things, and you've got a new richer expressive API for modeling things, you need a new algorithm for matching those. And so we've been implementing that, and then you need new ways to actually plumb those devices into your pod on the node. So a little bit of a visual of how that works. Kubelet plugin running on the node, so that's the green area there, that's the DRA resource driver. Just like device plugin works today, but instead of publishing just a string and a number, it publishes to the allocatable of the node resource, it publishes its own resource slices, which are independent resources you can list with kube control and whatever. It publishes those in well-defined, built-in upstream APIs so that kube scheduler, external schedulers, and autoscalers all can interpret and understand the same API. Rather than using custom resources for each vendor's type of device, we create a modeling API that all of the vendors use so that these upstream components can interpret the same data and make the same kind of decisions. On the request side, you can see that the pod spec gets a new entry under resources, requests, limits, and claims. Claims is just a reference to resource claims, which are these objects. And you can see that's not just a string and a number. It's a pretty sophisticated thing. You can actually request different types of devices and then add constraints. So you can say, I want a GPU and I want a NIC, and I want them both under the same PCIe root, which allows GPU direct to work, for example. You can't do that, anything like that with device plugin today. So how does this apply to what Bo was talking about? Because I'm talking about all this, like how we select devices. Well, it applies especially in scaling cases when we combine it with an advanced autoscaler. So an advanced autoscaler means something like Karpenter or Google has something called custom compute classes. And what these do is they allow you to put that optionality, like the DRA lets you be flexible in how you ask for, the workload asks for the devices, and these custom autoscalers allow you flexibility in what kind of devices what kind of nodes the infrastructure delivers to you when it autoscales. So by combining these two things, they're sort of like two sides of a coin. One is the workload needs to flexibly ask for things, and the second thing is the autoscaler needs to flexibly provide different types of nodes. And we'll see a demo of that in just a second. So as I mentioned, Karpenter is one way of doing this, and Karpenter hasn't yet implemented all of this functionality, but I know they're working on it, and they've been involved in the DRA project for quite some time. I'm going to demo it with custom compute classes from Google, and what you'll see is that that the flexibility in the workload specification allows us to avoid. Remember, Bo said you can use one A100, two L4s, or three T4s. Because we have different counts of GPUs, we needed different deployments, and therefore we needed to manually track quota and availability of different types of GPUs to know which deployment to scale. And that's a real headache. With these sophisticated autoscalers, they can track all of the information for us, but I need my workload to be able to flexibly receive 1, 2, or 3 GPUs and know what to do with that. I have no way without DRA to tell the pod spec, give me some number of GPUs. I just have to, with device plugin, I have to ask for exactly 1, exactly 2, or exactly 3. So going to the demo, in DRA, we can specify a resource claim. This is my resource claim template. And one interesting thing you'll see here is that this allocation mode says all. It doesn't say give me 1 GPU, 2 GPUs, 3 GPUs. It says give me all the GPUs on the node. So that'll get automatically, if your node spins up and it's got 1 GPU, the pod will show up and that container will have 1 GPU. If the node spins up and it's got 12 GPUs, then that pod will get 12 GPUs. That allows me to create a single deployment, that you see here, and it references the resource claim, and that single deployment then, as it scales, each node that comes up to satisfy the pending pods may have any variable number of GPUs, but that pod will land on that node and get all of those GPUs. So let's give it a try. What I have here are two screens. This first screen is showing nodes, pods, and then it just grabs the first pod that's using T4s and the first pod that's using L4s, and we'll show there's nothing running now. And I have another screen here that's just showing me the VMs. So I'm going to scale my deployment. Let's scale it to 5. Right now there's none. And what we'll see is pretty much immediately we see 5 pending pods. These 5 pending pods are basically each one is asking for it can't be met because it's there's no node out there that can schedule it, so it's pending. So the cluster autoscaler will kick in. It will look at that pod and it'll say, okay, that pod needs GPUs. In this case, I've pointed to a custom compute class. I forgot to show you that. My custom compute class, and while we wait for it to scale, my custom compute class says any workload, I put this on my deployment, and it says any pod that spins up, put it into this custom compute class, and it will give a preference to a T4 node, which is cheaper, and then if it runs out of T4s, it'll give a preference to an L4 node. So what we should see over here is that as these pending pods are seen by the cluster autoscaler, virtual machines will get spun up. So here we see 5 different virtual machines have gotten spun up by the cluster autoscaler, but you'll notice there's actually 2 different types there. And the first 3 are the T4s, but my node pool is limited to 3. So once it hits the limit on that node pool, I didn't have to track any of that. Compute classes track that for me. It says, oh, you've run out of T4 nodes. I'm going to start giving you L4 nodes, and those are the 2 we see there. We see them, now they're starting to be registered to Kubernetes. Those were the VMs. Now these are the nodes as they get registered. Pods are still pending. But what we should see within a couple of minutes is that the pods will come up, and this will start showing logs of some of those different pods, and it'll show us my workload. All it does is print out the GPUs that are seen by the pod. So we'll see whether we get the right number of GPUs in each one. Okay, so first one came up. It's still starting, but we are loading, and very soon. Should come along any second. Well, you can see them all, the additional pods coming in here as all the nodes have become ready. And now it looks like it's finding a pod that's assigned to an L4 node, but the container hasn't come up yet. Oh, okay, they've come up, and now they're waiting for, there we go. So what's happening here is you can see that even though we just scaled a single deployment, we had a single pod spec, the custom compute class, the advanced autoscaler, made a selection of the types of nodes to spin up to satisfy those pending pods, and then the pending pods themselves, because of the DRA configuration, those containers were able to come up and make use of whatever GPUs they were given. So your workload, of course, needs to adapt to whatever GPUs it sees, but most of these workloads already are able to do that. So the really missing glue was the ability for Kubernetes to plumb in different numbers of GPUs based upon whatever node was spun up. And that's the demo. And I think we have some time for questions. Yes. By the way, you can try this yourself. I have at this link here, which just wrapped a little bit onto the other side, unfortunately. I have those YAMLs, not exactly the ones I demoed with, but basically the same thing with a README on how to do it in Google Cloud, at least.
Yep. Hi. So my question is, so just now I think the demo, I came in quite late, but I saw it's on the kubelet level. And then I'm just curious, like, is this DRA and then everything, you can use it with a virtual kubelet? Let's say I have a virtual kubelet that probably actually calls an API to a GPU provider. So is that applicable like this to use it with a virtual kubelet?
So we have some, I'm not sure exactly, I mean, maybe. It would be interesting to investigate. We have some interesting features. So DRA is very, very active development right now. What's going to beta is just the very minimum viable product, basically, and you can do what I'm showing you here with what's going to stable, I mean. But we have some other things like there's a current enhancement proposal called binding conditions, and what it allows the driver author, not the user, but the driver author to do is kind of pause. The pod gets sort of partially scheduled, and the node gets selected, and then it can pause there while the back end, say, attaches the GPU to that node. This is for the disaggregated composable infrastructure that was discussed earlier in the keynote. And it allows then that, and once that succeeds, it proceeds with the scheduling the pod. So I think for a virtual kubelet type environment where you similarly have maybe some provisioning that needs to be done in response, you might be able to use that feature. But it's really, we would have to look at the details.
Thank you.
Other questions?
Thank you so much for your great presentations. And it might be a very basic questions, but I am interested in the status of the drivers vendors support of the DRA resources, because I quickly researched and I find the NVIDIA driver is now actively developing. So I'm interested in the status of that.
Great question. So the question was, what's the current vendor support for DRA?
Yes.
Yes. So, well, at Google, we have a number of DRA drivers we're working on. And at NVIDIA, there's a couple of them as well. And IBM is working on some. So, we're not GA yet with DRA in upstream. And so neither are the vendor's drivers. But I do know we're talking with the folks at NVIDIA and us at Google, we're working hard to line that up as closely as possible with at least some of these drivers will be fully supported with the GA of the DRA upstream base functionality. And then we're targeting like end of year for a lot of the other ones. But obviously each vendor, it's up to them. And even at Google, we have like 4 different ones. So some of them are in different schedules. But we're working hard with the goal that, say, early next year, or certainly by mid next year, we can really kind of transition everybody to the new DRA drivers as much as possible.
Oh, that's cool. Thank you.
Yeah.
And on this one, just quickly, I think there's one additional aspect of your question, which is hardware vendors like NVIDIA is also embracing this model very strong. And because they see the benefits that this will not only help developers to consume these accelerators in a much easier way, and then in turn, it's going to benefit these hardware vendors as well. So that's, as John mentioned, NVIDIA is also working on their driver. We're working on this very closely, and then I think they have strong reason to push this as well. We want to make this as an ecosystem success, including cloud vendors and hardware vendors, and also, of course, the Kubernetes community. Yeah.
I see. Thank you so much for detailed answers. Thank you.
Sure. Yeah.
Hi, I'm from SAP. So my question is about NVIDIA drivers. There's something called the partitioning. So you can partition the drivers into smaller units, and then that's called virtual GPUs. Is DRA supporting this, or is the features going to be on it?
Great question. Yes. So that's actually one of our one of our big use cases. So DRA, that flexibility in modeling devices, one of the things, we have a cap called partitionable devices, and it's being used for NVIDIA MIG is one of the use cases. And basically, we talked about flexibility in request. So if I have a request that says, I need any GPU with at least 8 gigs, the way that the partitionable device modeling will work is that with a request like that, you could actually get an L4 that's out there running, because that's all you ask for, or you could get a partition of an A100, and the scheduler makes the selection, and then once the scheduler makes the selection, that gets the sort of DRA aspect is it's smart enough to say, oh, you grabbed this partition, that makes all these other partitions that overlaps with unavailable for the next pod that comes in. And so it allows us to avoid overscheduling, and it also allows us to dynamically partition. So that's definitely, it won't be there in August. We're trying to make beta for that in August, but it's alpha right now.
Okay, then my second question is that the NVIDIA drivers also has something called time slicing the GPUs itself. So it's not just virtual GPU, there's also a time slicing so that you can run more pods on different models, but it's time slicing the GPU into different models. So is that also part of the DRA?
Yes, it is. So we only talked about a tiny piece here because we didn't want to make it just about DRA. It's more about the auto-scaling aspect of it. But DRA allows you a couple of different ways to do that. One is you can attach configuration to any of these requests. So rather than actually the request just being like, I want flexible, you could actually say, I want this type of GPU, and here's a vendor-specific set of configuration I want you to apply to that device after you plumb it into the pod. Now, the driver does all that for you. But that, for NVIDIA, can include, for example, a time slicing configuration. So you could say, hey, I'm going to configure this GPU as time sliced, and then I can point multiple pods or multiple containers at the same resource claim, which points it at the same GPU. So that's what we call user-mediated sharing. The user has to be very careful about which pods and containers they point to that GPU. Now, some folks here are working on another feature that's hopefully will be alpha in 134 for what we call consumable capacity. That allows you to shift the decision of that sharing from the user to the platform and let the platform mediate that sharing. How that exactly works with time sharing would be dependent on how NVIDIA sets up their drivers, but you should theoretically be able to implement that. The upstream components will be there to implement that, but NVIDIA would need to implement some things in their driver to make it work.
Thank you.
Sure. You have another question?
Thanks for the demo and the insights. I really like the whole demo and the philosophy behind. I have a quick question regarding is there any thoughts around supporting the similar mode but extend that to a multi-node scenario?
Okay, we just have 1 minute left. Great question, another great question. So multi-node is actually within scope of DRA. So we're using it, so we talked about partitionable MIGs, like for a single GPU breaking it into multiple GPUs. We actually at Google are using DRA and the partitionable devices to represent logical multi-node devices, which we call TPU subslices. So you could have, say, 4 nodes, each with 4 TPUs, that's 16 TPUs. Well, you could consume 1 node, or 2 nodes, or all 4 nodes. And we're using the same partitionable model that represents overlapping things to model those logical devices and sort of improve the ability to manage multi-node workload requests. You could extend that to auto-scaling. We haven't quite gotten there yet, but definitely multi-node, these resource slices, actually, when you publish a resource slice, you can say not just it's on this node, you can say it's accessible from any of these nodes. And in fact, with the partitionable model, for each logical device within each partition, you can say which nodes. That's how we're doing it with the TPE subslicing. You can say this subslice, this logical device, is accessible from these 4 nodes, or really consists of these 4 nodes in that case. So yes, the short answer is yes.
Gotcha. Thank you.
Thank you. Okay, I think we're out of time. Thank you all very much.